Hello folks, StylePoint here, and today we're going to be discussing gradient descent. I thought it would be good to make a video about this because we already used gradient descent in two of the videos, namely in the linear regression implementation as well as in the logistic regression video. So I thought it would be a good addition to the series. And we're going to be discussing gradient descent as well as discussing three major flavors of gradient descent, three primary variants that we usually kind of discuss when it comes to gradient descent. These are batch gradient descent, stochastic gradient descent, and mini-batch gradient descent. And so gradient descent in general, that's a optimization algorithm, and it's widely used for training machine learning, deep learning models. So it's kind of become very popular in that kind of thing where we train models pretty much. There are other ways to train models, but this is the most popular one, especially for deep learning models. And as already mentioned, we have three different flavors. Now, before we're going to dive into that, let's also look at the definitions here. So we have definitions of different, functions and parameters. We have theta for representing model parameters. We have the loss function, j of theta. We have gradient of the loss function with respect to the parameters theta, learning rate, that's alpha, and the mini batch size. And let's start with the batch gradient descent. So before that, actually, how does gradient descent work in general? Well, usually the way it works is that we iterate over the data set some number of times. That's called epoch. Well, the number of times we iterate over the data set is represented by usually a variable called epochs. A single epoch is a single pass through the entire data set. Now, it could be that a single epoch does not really represent we do not really go through the entire data set. Sometimes that can be possible. Sometimes it can be useful to do that. In that case, we may have some other parameters like step size. So in a single epoch, we're not going to go through the entire data set. Instead, we're going to go through maybe a portion of the data set, and maybe we're going to shuffle the data set at the beginning of each epoch and do it that way. But for the sake of simplicity, let's assume that for every epoch, we're going to go through the entire data set. And so let's suppose we have some number of epochs. Well, in gradient descent, for every epoch, then we go through the entire data set and perform optimization. Now, we start with batch gradient descent. How does that work? Well, for every epoch, we do go through the entire data set, but even more, we use this entire data set for updating model parameters. So we pretty much shove the entire data set into the model and update model parameters that way. Okay, and so the entire data set is used for parameter updates. Now, right away, we can notice that it can probably kind of cause some problems. It will not allow for online learning. It's one of the drawback of this approach. In other words, it does not really allow for efficiently updating the model with the new samples on the fly. So let's suppose we have some data set that we trained using batch gradient descent. So we had some number of epochs, and for every epoch, we use the entire data set for updating model parameters. Now, let's suppose some new data came in. Well, we cannot really train the model on this new data because it's, in this case, with batch gradient descent, it's not designed to be trained that way. So what we need to do is that now we have to merge the old data set, whatever we had, with the new samples, and now train the data set that way. And so train the model that way, sorry. And so it does not really allow for only retraining maybe like a worm-started or pre-trained model only on the new samples. We have to pretty much merge the old data set with the new one and train that way. And so we can see how that can be problematic. Of course, that can lead to some memory issues because if we get more and more, as we get more and more data, we can potentially run out of, we may have problems basically with running out of memory. And of course, we could go and buy more memory and maybe buy new hardware, but of course, that's not the kind of scalability we're looking for. Now, the good thing about batch gradient descent, one of the pros, is that it kind of converges. It's almost guaranteed that it's going to converge to the global minimum for convex functions. And for non-convex functions, it's going to usually converge to the local minimum. For what I call a reasonable learning rates, that basically means if the learning rate is not too high, basically. And here's the formula for updating model parameters. So parameters equal parameters minus learning rate times the gradient of the loss function with respect to the parameters theta. And this is done. This parameter update again is done over the entire data set. So it's well, the input is the entire data set, and the updates are done that way. Now, to discuss what is convex and non-convex function, I already generated a matplotlib plot, and discussing that, we have this blue plot, this blue function. That's a convex function, and we can see it's kind of a nice function. It looks like parabola, and I think in fact this is a parabola. So it has one global minimum, okay, and so it's kind of easy to optimize on this kind of surface. It's easy to do optimization. On the other hand, if we look at the non-convex function, this red function right here, well, in that case, we can see that we have a lot of dips here. We have a lot of local minima. So we have like it seems like this is the global minimum. Then we have a local minimum here, another local minimum. There's another one. There seems to be. This is like another global minimum, so we have like two global minima. So it's like the optimization, the surface basically of this is a lot more complex to optimize on. And with batch gradient descent for convex function, it's usually with batch gradient descent, we're usually going to converge to the global minimum because there's usually only one. But for non-convex functions, we're likely going to converge to some kind of a local minimum, maybe this one right here. But it's usually unlikely to converge to the global minimum due to the nature of the algorithm. And of course, the fact that with batch gradient descent, because we're inputting the entire data set and updating model parameters that way, we do not really have a fine-grained control over the samples. We do know the behavior of the model, behavior of loss when it comes to the entire data set, but we don't know how every sample or maybe some number of samples contribute to this loss. And so we don't really have a great control over how the training is going to go. Although yes, I mean we can fine tune some parameters, we can configure, tweak, learning rate, things like that. We can use grid search and so forth, but still. We don't really have that control. Now, moving on to the stochastic gradient descent. Stochastic gradient descent takes almost like an opposite approach. So instead of saying, oh, I'm going to use the entire data set for updating model parameters, stochastic gradient descent says, I'm going to use a single feature label pair for updating model parameters. Okay, so it's like the opposite. It's like the other extreme. Instead of using the entire data set, we use like a single feature label pair. And notice that I wrote for updating model parameters, so with S at the end. It's not always the case that a single feature label pair is going to update only a single parameter. In fact, a lot of times it updates more than one parameter, could be many. Okay, now right away we can see that this is actually cool because we can now do proper online training. We can update the model, maybe a warm-started or pre-trained model, with the new samples on a fly. So we don't really need to merge the old data set with the new one and train that way. No, we can have a pre-trained model that was trained on some old data set, and if the new samples come in, we can train this already pre-trained or warm-started model with the new samples on a fly. So that's super cool. So we're not going to be running into like memory issues with this. We can kind of scale that way. We don't really have that vertical kind of a scaling where we go and like buy new hardware. Now, the cool thing about this is also the fact that it's usually faster than batch gradient descent. Not only because we're doing this kind of a divide and conquer kind of an approach where we have maybe a big data set, we chunk it into individual samples or feature label pairs and train it that way. That's, of course, going to be a bit, usually it's faster basically, but also because of the fact that sometimes with batch gradient descent, if we're at the limit of our memory, whatever we have, let's suppose we have 128 gigs of RAM and we are at 126 gigs with our data set. Well, because we're at the limit, it can slow down the system. And with stochastic gradient descent, we do not really have that. Okay, so that's cool. Now, stochastic gradient descent, differs from batch gradient descent in terms of how the loss plot is going to look like, and also kind of the behavior at a particular point of the loss function. Because in this case, well, not behavior so much as in it's more of the values of the loss, because we're inputting a single feature label pair at a time. So that means it's going to learn new information pretty much every iteration. So in batch gradient descent, we had like some number of epochs that we would iterate over, and then for every epoch we're going to shove the data set into the model. In this case, we have a for loop for epochs and another for loop to iterate over the data set, over the samples. Again, we assume that we're going to iterate over the entire data set, but if we didn't want to do that, there are ways to, just maybe have some number of optimization steps into the data set. But again, for the sake of simplicity, we're going to assume we iterate over the entire data set. But in this case, because we're doing one feature label pair at a time, it's going to learn one feature label pair at a time. And so the loss values, they're going to fluctuate a lot. And we're going to have these high variance updates. Now, this can actually be beneficial in some cases. For instance, let's suppose we are in this local minimum here. Because we have these heavy fluctuations, it's more likely that we're going to jump out of this local minimum and converge to a better one than in a case of batch gradient descent. And so these fluctuations can actually help sometimes. Sometimes they can actually allow us to converge into a better minimum. In this case, it might not be, global minimum, but it could be a better local minimum. And it, in fact, could also be that we're here, and now because of these heavy fluctuations, we're going to jump out of this local minimum and converge to a better one here, which is one of the two, it seems, global minimas. So that's super cool. So it's kind of like a feature that comes with a stochastic gradient descent. And we can see the formula here. Theta equals theta minus alpha times the gradient of the loss function with respect to the parameters theta. And we see here we have xi, yi. In case of batch gradient descent, we didn't have that. I didn't put that there because we're using the entire data set. But in this case, we use a single feature label pair at a time. So we put xi, yi. Now, finally, like the most popular flavor of gradient descent that is used for deep learning and machine learning, that's what we're going to be using actually, is mini batch gradient descent. And it kind of has the best of both worlds, of both the batch gradient descent and stochastic gradient descent, because in case of mini batch gradient descent, we don't take like a single feature label pair at a time, but we also don't take the entire data set for updating the model parameters. Instead, we take some number of samples, and we call that mini batch, or sometimes it's referred to as batch. Just remove the mini, just so that it's easier to, it's just shorter version of it. But more formal, it's a mini batch, because batch gradient descent, we know we use the entire data set there. So mini batch gradient descent, we have some number of samples for updating, for every optimization step, for updating model parameters. And so I put that it's usually from n equals 8 to n equals 512, so from 8 to 512, and it's usually a power of 2. You can put whatever, you can put 25 as well, or 36, but usually it's power of 2. And again, I don't really have a reference for this. I've seen actually batch size. I've used batch sizes more than this, but usually it's from 8 to 512. I think that's a reasonable range. Of course, that also depends on the system. Sometimes, depending on the data, the kind of data we have, we might not be able to load more than 64 feature label pairs at a time. So this is kind of like a hyperparameter in a way that we can configure as well. Now, mini batch gradient descent, we could see that, we could look at this as kind of like a generalization of both as well. Because if we set n equals 1, we're going to pretty much get like the stochastic gradient descent. And if we're going to set n equals to the size of the entire data set, then we're going to get the batch gradient descent, right? So it's kind of like a generalization of both, and we could think of stochastic and batch gradient descent as special cases of mini batch gradient descent. That could be helpful maybe to think about it that way. Now, of course, mini batch gradient descent would allow for online learning or online training, and we will be able to update the model with new samples or new examples on a fly, again, because we can warm start or pre-train our model, and then if the new samples come in, we can just retrain the model on these samples alone without having to merge the all data set with the new samples and train the model that way. And so super cool. In addition to that, we can also leverage highly optimized tensor operations. We usually run deep learning and machine learning models, or train them. We run the training on GPUs or TPUs. So GPUs, these are graphics processing units, and TPUs are tensor processing units. And TPUs, of course, they're designed specifically for tensor processing. That means performing tensor operations like tensor dot product, addition, broadcasting, things like that. GPUs are also super powerful. Of course, those are used all over the place in gaming, in games where we update. So GPUs are basically super efficient for making small computations very quickly. So like updating frames and things like that we get in games. And so with mini-batch gradient descent, because we have a reasonable, usually mini-batch size, like maybe 32 or 64 or 16, something like that, we can leverage GPUs and TPUs. And those are going to allow us to perform these operations like multiplications and tensors and so forth very, very quickly, very efficiently. And usually, mini-batch gradient descent is as fast or faster than stochastic gradient descent. So that's super cool. And so in general, batch gradient descent is the slowest one. And then we have stochastic gradient descent and mini-batch gradient descent, right? So mini-batch is, again, usually as fast or faster. And so that's great. Now, in case of batch gradient descent, even if we use GPUs or TPUs, because we're passing the entire data set, we're loading that onto the TPU or GPU or doing inference that way or doing training that way, it would not be as efficient. That has to do with the way GPUs and TPUs work, but it's always better to have a more reasonable batch size. And so if we have gigantic data sets that we load onto GPUs, it may be better to train the model on a CPU, actually, in that case. So using the central processing unit. But yeah, we can leverage these highly optimized tensor operations because we have this reasonable batch size. Now, it also reduces the fluctuations that we see in stochastic gradient descent because we don't really take a single feature label pair. Instead, we take some number of samples, and we call that a mini batch or a batch. In case of batch gradient descent, of course, we will not have those heavy fluctuations because we can think of a loss there as if it's like averaged over the entire data set. In case of stochastic gradient descent, we have a single feature label pair. We calculate loss that way. We have heavy fluctuations. In mini-batch gradient descent, we might still have fluctuations, but we're not going to have them as pronounced as in stochastic gradient descent because it's somewhere like in between batch and stochastic in a way. Now, the problem, though, the cons of this approach is that it usually does not guarantee a good convergence out of the box. And so we may need to utilize some advanced approaches for that. And I'm going to briefly touch onto them as well. I'm probably going to make videos about them as well. But so this is the optimization for this approach for mini-batch gradient descent. So parameters equal parameters minus learning rate times the gradient of the loss function with respect to the parameters. But now you see we have from I to I plus n. So that's a batch pretty much. I to I plus n. Start including I, not including I plus n. So that's the way it basically works. Now, as already mentioned, we usually use some more maybe advanced techniques. So here's one example. Let's suppose we are using mini-batch gradient descent and we're converging to this. Let's say we're moving out of this local minimum and trying to converge here, and we're moving toward this direction. So it's kind of a better local minimum. Well, if we know we're moving the right direction, maybe we can speed this convergence up. And so there is a parameter that we can add called momentum that's going to increase our momentum in a way, and speed up convergence. Now, sometimes, just like with these fluctuations, in stochastic gradient descent, fluctuations can help, but it could these fluctuations could also be detrimental. Maybe we're here and we're going to jump out of it and jump to a worse local minimum, and so that can be problematic. So momentum is kind of like that. We're speeding up the convergence instead of having fluctuations. We have a kind of this kind of maybe like an acceleration. We could think of it that way, but we can like overshoot. And to mitigate that, there is another approach called Nesterov's accelerated gradient, which has this kind of a look ahead and sees, am I gonna overshoot? If I'm gonna overshoot, I'm gonna be more careful about that. Then there are other approaches like RMS prop, which assigns individual learning rate to every parameter. There are other approaches like ADAM as well, and weighted ADAM, and those are pretty much like RMS prop plus plus the momentum. So we assign individual learning rate to every weight or parameter, and then we also have momentum as a parameter. So there are various approaches that we can utilize to efficiently train using mini-batch gradient descent and have performant deep learning or machine learning models. And so this is going to be it for this video. I hope you found it helpful and informative, and I'm going to see you next time.